All right, everybody. So this video is regarding the named theorems. Sorry about that. I'm starting on page 48. There are several key levers here, but I should be able to go through them pretty quickly since most all these theorems have been hit in other topics that we've gone over. So our first big key lever and big theorem is the IVT. I haven't snipped the whole statement of the IVT. I just grabbed the model problem over here, but it's right up above on page 48 if that's where your packet is. So we have a function that's continuous and we are looking at a few data points from that function in this table. And the question is, what's the minimum number of solutions to f of x equals 7 on the interval 1 to 4? Justify your answer. So basically what this is communicating to us is that I have a function that's continuous, which means I cannot pick up my pencil as I move from one point to the next given in this data table. So if my first point is expressed as 1, 6 and the second point is 2, 9, just visually speaking, in order to get from 1, 6 up to 2, 9, I'm going to have to cross 7 in between those two outputs. As I keep moving, the next point's at 3, 10. So based on this data alone, it would appear as though I go up a little bit more to get to 10. It's not guaranteed I would cross 7 again. But then at the end, to move from 3, 10 to 4, -1, I would have to cross over that 7 again to connect to those two outputs. So I'm looking for the guarantees. Where do I have to cross 7? And I have to cross 7 between these outputs of 6 and 9 and between the outputs of 10 and -1. So the way that we formalize this is to state the conditions of the theorem and then explicitly mention what's significant about that data that guarantees a solution of 7. So I'm going to start with, since f is continuous, IVT applies. That's a blanket statement that we need to give at the beginning to capture our condition, and then we can get into the root of this problem. So since f of 1 is 6, and that's less than 7, and f of 2 is 9, which is greater than 7, that means f of x must equal 7 on the window 1 to 2. I'm just showing that one endpoint is less than 7, the other is greater than 7, so of course the function equals 7 somewhere between those 2 points. I'll do the same thing for the data for 3 and 4. So since f of 3 is 10, which is greater than 7, and f of 4 is -1, which is less than 7, my function must equal 7 on this small window of 3 to 4. So what's the minimum number of solutions? Therefore, the minimum number of solutions is 2. Could there be more than 2 solutions? Yes, but I'm guaranteed to have at least 2. Perfect. Our next key lever is L'Hopital's rule. So this is also one that we've gone over, and I'm going to push us on the new notation that I expect to see when we use L'Hopital's rule. So I've got a limit as x approaches 0 of the root of x plus 4 minus 2 divided by x. I want to split this into numerator and denominator and show that the limit as x approaches 0 of the square root of x plus 4 minus 2 is equal to, let's see, the square root of 0 plus 4 minus 2, or the square root of 4 minus 2, or 2 minus 2, 0 on top. And I want to show the limit as x approaches 0 of the bottom, which is just an x, direct substitution, I get 0. So since my numerator and denominator have limits approaching 0, I can say L'Hopital applies and get right to the conclusion of L'Hopital. By L'Hopital, I can record this as a new limit of the ratio of the derivatives of those two functions that I see on the top and the bottom. Derivative of x, I'll start there, that looks easy, is 1. And the derivative of the square root of x plus 4 minus 2 is 1 over 2 square roots of x plus 4 minus the derivative of 2 is 0. So now by direct substitution, my answer here is going to come from plugging in a 0 into the L'Hopital limit, and I get 1 over 2 square roots of 4, or 1/4. Key lever number 3, the mean value theorem. Remember, that's the one that shows that if we have a continuous and differentiable function, then our slope on a given interval is guaranteed to equal the derivative on that interval, somewhere in that interval. So I've got a function here, square root of 9 minus x squared on the interval -3 to 0. For my visual folks, square root of 9 minus x squared is the top half of a circle. I want that curve only from -3 to 0, so I'm looking basically at the left-hand side of this semicircle right over here. That looks like a continuous differentiable curve. So what I want to try and do is show that the slope between my endpoints, -3 and 0, is the same as the slope of some tangent line within that same interval. So the first thing I want to do here is show that I know how to find my slope. That's f of 0, change in y, minus f of -3 over my change in x, 0 minus -3. If I plug a 0 into this function, f of 0, I'll do my side work up here, that's the square root of 9 minus 0 squared, or 3. And if I plug in f of -3 into my function, that's the square root of 9 minus -3 squared, or 9 minus 9, so I get 0 up top. I do some simplifying down here, and it's 0 plus 3 in my denominator. So 3 over 3 gets me to a slope of 1. And based on just my rough sketch alone, I kind of believe that. The slope of that initial red line I drew looks like 1. So I know, based on my mean value theorem, that the derivative of this function is guaranteed to equal 1 somewhere on that window. Well, what is my derivative? Let's make sure we uncover what that is. F prime of x is 1 over 2 square roots of 9 minus x squared times -2x. That's the derivative of the inside function. Cleaned up, that looks like -2x over 2 square roots of 9 minus x squared. Or maybe I can cancel those 2's. -x over the square root of 9 minus x squared. All right, so I've got my pre-work done. I know the slope between my two endpoints. I know my derivative. MVT states that those two things are guaranteed to be the same. So -x over the square root of 9 minus x squared must equal 1. Got to dig in and do some math here. So I'm going to multiply that square root of 9 minus x squared on both sides to get rid of the fraction that I see. Those cancel. So I'm looking at -x equal to, let's see, the square root of 9 minus x squared. I'm just going to keep doing math now until I can get to my answer. So I'll square both sides to get rid of that radical. That leaves me with, let's see, x squared, negative goes away when I square, equal to 9 minus x squared. I'll combine like terms, 2x squared equals to 9. Come up here where I have a little bit more room. I'll divide by 2. X squared is 9/2. And I'll square root, and I get the radical of that 9 over 2. Got to be careful because currently square root of 9/2 is a great answer, but it's not in my window. It's a positive square root of 9 over 2. That's somewhere over here outside of the problem that I'm considering. So I have to be really mindful that when I square root, we can't forget I get plus or minus. And in this problem, the solution that's relevant is actually the negative square root of 9 over 2, because that's the window that I was given on that left side of the semicircle. But here it is. I've found the value right around here where my tangent line is parallel to my secant line, where my slopes are the same. Okay, the extreme value theorem states that if we have a continuous function, we're guaranteed to have an absolute max and an absolute min on our closed interval. And most of the time, the College Board requires us to find those values, the absolute min and the absolute max. So to do that, side note over here, we want to make sure we're finding our critical points and our endpoints, those are always given to us in the problem, and uncovering what our function's y values are at those significant places. To find critical points, that's when our derivative is equal to 0 or undefined. So that's the big bulk of the work I have to do. Let me come over here and find my derivative function. That's 3x squared minus 12. That's a quadratic equation, so it's never undefined, which means I won't have any of that to consider, but that definitely equals 0 in a couple places. When 3x squared equals 12, or when x squared equals 4, or when x is equal to plus or minus 2. I'm going to be careful here when I continue on with my work. I'd love to test my endpoints in my original function, f of -1 and f of 3. And it looks like I have 2 critical points over here based on my side work off to the side. But -2 is actually not in this window. So I'm only going to test the critical points that fall in the given interval, because that's the only location that I'm concerned with in this particular problem. So now I just want to go find the smallest output, since we're being asked for a minimum value here. So this is just going to be some number crunching. I want to take -1 and plug it in to our function, see what I get. So that's -1 cubed, or -1, plus 12, that sends me to 11, plus 8, I get 19 for f of -1. I'm going to do the same thing at 2. That's 2 cubed minus 12 times 2 plus 8. Let's see if I can do this one in my head. That's 8 minus 24, so that's -16, plus 8, that lands at -8. One more, I'm going to plug in 3. 3 cubed, oh dear, minus 12 times 3 plus 8. That's 27 minus 36. 27 minus 36, -9, plus 8, -1. So the absolute minimum value of this function is -8, since that's the smallest output that we see when we run through the application of the extreme value theorem.